So last couple classes, few weeks, we've been dealing with flow over bodies, so over a flat plate, over circles and spheres, cylinders, last class. Now we're going to deal with flows inside of things. So I have laminar tube flow, so flow through a pipe essentially. I'm going to assume this is fully developed, steady, pressure-driven flow through a pipe. So we end up with a nice parabolic velocity profile. You may remember that from fluids class. Maximum velocity U0 down the middle. I'm assuming for now I have a constant wall temperature, so TW, my pipe wall at some constant temperature. Just assume the entire wall is at that temperature TW, so this TW is really at my inner radius R0, so only inner radius I care about. That's where the fluid and pipe are in contact with. So that is where we're going today. So the velocity profile in the tube, again going back to kind of fluid mechanics, we have this relationship that my velocity at any point, so R being my radial coordinate from the center, R0 the actual inner radius of the pipe. U is 1 over 4 mu, so viscosity, pressure gradient dP dx, R squared minus R0 squared. You can see this is going to have a maximum value when R is 0, given by minus R0 squared over 4 mu dP dx. Also going to be 0 when R equals R0, so again, no slip condition on the walls. So that's my velocity profile inside the pipe. So assume you have a constant heat flux, so that Q, the heat being transferred down my pipe, is constant, so it doesn't change down the pipe, so I have the same Q values everywhere down the pipe. Then I want to perform an energy balance on the pipe, so energy being convected away from the fluid is equal to the energy being conducted through the pipe wall. We get this equation, so 1 over velocity U times R, d by dr, R dt dr is 1 over alpha dt dx. And then using the velocity profile we had on the last page for U, stick that in down here, ends up over on that side. Get d by dr, R dt dr is 1 over alpha dt dx, U0 R 1 minus R squared over R0 squared. And now I want to integrate this guy to find the temperature distribution. One thing to note when we do this is that this value dt dx is a constant, so even though this looks kind of nasty, it's not that bad because this is a constant based on this equation, or this assumption here, so that'll make our lives easier when we do that. So the equation we had, slightly cleaner form, d by dr, R dt dr is U0 over alpha dt dx. Then I put the R inside the parentheses, so I have R minus R cubed over R0 squared. Again, integrate this guy, so that derivative goes away. I'm just left with R dt dr. On this side, this stuff's all constant, so U0 over alpha dt dx. Integral of R is R squared over 2. Integral of R cubed is R to the 4th over 4. R0 squared is still there. Then I get a constant from that first integration. Now divide by this R, so that R goes away. I'm left with just an R for this guy, R cubed for that guy, and C1 over R there. Then one more integration gives me my temperature distribution that I'm looking for. So these constants, U0 over alpha, dt dx, R squared over 4, minus R to the 4th over 16, R0 squared. I have C1 natural log of R, and my second constant, C2. Now to find those constants, I need the boundary conditions. And so I have kind of an implied boundary condition at R equals 0 that I can't have an infinite temperature. So if I stuck in R equals 0 to that guy, I'd end up with negative infinity. Again, don't know what the temperature necessarily is there, but I know it's not negative infinity. So I have to set C1 equals 0 to avoid that happening. And then if I do have R equals 0 here, I end up with 0 essentially. And so all I'm left with is C2. As I said, I don't necessarily know what that temperature at the center is, but I'm just going to call it TC for now. So then C2 just becomes TC, the temperature at the center of the pipe. So with all of that, the temperature distribution in the pipe has this form, so T minus TC is 1 over alpha dt dx, U0 R0 squared over 4, R over R0 squared, minus 1/4 R over R0 to the 4th power. So clean that up a little bit, that's what it looks like. So now I know the temperature pretty much anywhere inside my pipe as a function of R. Now, convective heat flux for pipe for internal flows looks very similar to what we had for the external flows. The main difference is when I have my equation, Q over A, H, T wall, instead of having T infinity, I have a TB, which means the bulk temperature. So the external flows, I looked at what temperature was flowing over it. For the internal flows, I need kind of an average value of the temperature through the pipe, and that's unfortunately going to change as you go through the pipe. So if I come into my pipe's really hot, it's trying to heat up the fluid. As I go down the pipe, that average temperature of the fluid is going to get hotter and hotter as you go down. And so basically what we need is some sort of average. So if we take that and find kind of an average value down the pipe, we end up with this equation for the bulk temperature, center temperature plus 7 over 96, U0 R0 squared for alpha times dt dx. So again, you can see in that it depends on how the temperature changes with x. So with that, we can also find the wall temperature. The wall temperature, essentially, I just look at my temperature distribution we had and stick in R equals R0, because that is where the wall is. So we stick in R equals R0 to that temperature distribution. We end up with T wall is Tc plus 3/16, U0 R0 squared for alpha dt dx. So that's the temperature of the wall. Again, it's going to depend where I am down the wall. So obviously it's going to heat up or cool down as the fluid moves through it and takes heat away from it. The other thing I really want to know is what the temperature gradient is at the wall. So dt dr at R equals 0. Again, I can find that using that temperature distribution, take the derivative d by dr, and then set R equals R0. What we get from that is U0 R0 over 4 alpha dt dx. The reason I want that is because when I do my energy balance, remember my Q over A, I want to have the heat being convected out from the fluid equal the heat being convected through the pipe wall. So I can set up that equation. So Q over A, H, T wall minus T bulk, there's my convective term, equals K dt dr at R equals 0. There's my conduction term through the wall. And solve this for H, so again, that's what we're always trying to do. For the past couple weeks and the next few weeks, want to find the value of H. So value of H, solving this equation, gives me K over T wall minus T bulk, dt dr at R equals 0. Then plug in some of these equations, and that gives us 24 over 11, K over R0. Now normally when we deal with circular geometries, we deal with diameters instead of radii. So just change that to 48 over 11, K over diameter, D0, and there's my value of H. So for circular pipe flow, that's laminar, and all those other conditions we set out at the beginning, there's my value of H. Now again, the normal procedure is to find the Nusselt number, and so in terms of the Nusselt number is H times diameter over K. So take that value of H, multiply by diameter over K, that basically cancels out. All I'm left with is 48 over 11. So very, very, very simple formula for a Nusselt number. In this case, laminar flow through a pipe. Nusselt number is 4.36, and that is it. So the equation we just had, the Nusselt number equal 4.36. Important to note that's for the very specific conditions that we laid out in the problem. So it's for a circular tube, uniform surface flux, so same Q value coming in at every location, and obviously laminar, fully developed conditions on the inside. Now there's a lot of other conditions that we're going to deal with basically for the rest of this lecture. First one is another common heating condition, one where the surface temperature is constant. So instead of having the same Q all the way down the pipe, I have the same wall temperature all the way down the pipe. So that's going to involve different values of Q because obviously my fluid flows down, should be different temperature gradients, so different heat flux is necessary. So that's another situation we can deal with. Going through a similar analysis that we did previously, we can come up with a Nusselt number for that case, which is, again, a nice simple equation. Nusselt number 3.66 in this case. And of course, we still need laminar, fully developed, all that stuff as well for that guy to work. So another condition is the entry region. So entry region is where the fluid is not fully developed. So as it just enters the pipe, it's not yet fully developed. Eventually at some point it becomes fully developed and it's fully developed for the rest of the flow. but this in the entry region, so before that actually happens. Again, we have equations for the Nusselt number. So Nusselt number, be specific based on diameter, is 3.66 plus 0.0668 diameter over length. Reynolds number, again, based on diameter, just to be specific, because Reynolds number could be based on length or diameter, but usually in these circular problems it's diameter always, but just to be safe, diameter there. Prandtl number, 1 plus 0.04, again, D over L, Reynolds number, Prandtl number to the 2/3 power. Now these guys, obviously fairly complicated in the entry region, so these guys are done experimentally. Another decent equation is the somewhat simpler relationship down here. For Nusselt number, 1.86, Reynolds number, Prandtl number to the 1/3, D over L to the 1/3, and then you have viscosities, mu over mu wall. So again, this is the viscosity of the fluid at the, this would be at the bulk temperature, U, W would be at the wall, obviously, to the 0.14 power. This guy's only valid for this combination being bigger than 10, but either one should give you decent results. So another really common flow condition is that the flow is fully turbulent, so as opposed to being laminar, I now have turbulent, fully developed flow through my pipe. Equation in this case, obviously again comes from experimental values. Nusselt number, again based on diameter, 0.023, Reynolds number to the 0.8 power, Prandtl number to the power n, where n is either 0.4 if the fluid is being heated up, or 0.3 if the fluid is being cooled down. This equation, again experimentally determined, valid for Prandtl numbers between 0.6 and 160, Reynolds numbers above roughly 10,000, length over diameter ratio for my pipe bigger than roughly 10, and moderate temperature differences between the wall and fluid, so nothing too crazy in terms of temperature difference. So this guy is useful for pretty much all the turbulent flow in pipe situations we'll see in this class. There are of course other equations for other scenarios, but this one should suffice for this class. Other less common scenarios are first ones for non-smooth pipes. So if you have a rough pipe, Nusselt number for that case, again based on diameter, F over 8, Reynolds number based on diameter, minus 1,000 times Prandtl number, divided by 1 plus 12.7, F over 8 to the 1/2 power, Prandtl number to the 2/3 minus 1. F is the good old friction factor. You may remember that from fluids class. You found that from the big ugly equation or the Moody chart. So that's how you do that for rough pipes. The other one is if I have a non-circular cross-section, so instead of having a circular pipe, have a square duct, a rectangular duct, or some other shape. To do this, you need the hydraulic diameter. So hydraulic diameter D, should be BH, is 4A over P, so 4 times the cross-sectional area, so the area of that square or rectangle, whatever it is, divided by the wetted perimeter, so the area which is in contact with the fluid. Nusselt numbers for those cases, various cross-sections, table 8.1 on page 393 give you equations for those. So a note on the bulk temperature, in external flows we care about the free stream temperature T infinity. That is basically our temperature that we're comparing to. As we're flowing across these plates, that temperature is very much prominent on the outside of the plate. Yes, in the boundary layer it changes, but the boundary layer is fairly thin that overall we still have this T infinity flowing over for a very, very long time. Doesn't necessarily happen in tube flow, because in tube flow, as they come in, boundary layers converge, and that's when it's fully developed. So when the boundary layers converge, I no longer have any sort of free stream temperature because I'm inside the boundary layer no matter what. So because of that, we need some other sort of average temperature, and that's where the bulk temperature comes in. It's basically what the temperature would be in thermal equilibrium. So if you let the thing, all the temperatures diffuse into one constant temperature, that's what the bulk temperature is. For that reason, it's also called the mixing cup temperature. And so that's what we need to use for our comparison for these heat transfer purposes instead of T infinity. So in addition to the energy balance that we did from the fluid being convected through the pipe and the heat being conducted through the pipe wall to find H, also have to think about the fact that this heat transfer is being transferred into the fluid, and so I'm going to have some temperature difference as my fluid goes through. it's going to be heated up or cooled down. That's going to involve some heat transfer as well. So I'm going to have some energy added or removed from the fluid, and that can be expressed in terms of the bulk temperature difference. So as my fluid comes in, it has some bulk temperature, some average temperature as it's coming in, has some other average temperature, TB2, as it goes out. So there's a temperature difference that the fluid got heated up or cooled down, and so that heat transfer, m dot Cp times that temperature difference, is how much heat had to be added or removed. In that scenario, it's going to be equal to the convective heat transfer rate, so Q HA T wall minus T bulk, and here I have a little average there because again, as I move through this pipe, I'm not sure what my heating condition is. Is it the constant wall temperature or is it constant heat flux, in which case T wall is going to vary down the length. TB, as we just mentioned, also is going to vary down the length, so I need some sort of average value for that to give me the heat transfer there. So time for some examples. First example, we have water flowing through a 2.5 centimeter diameter pipe, Reynolds number of 1500, and a bulk temperature of 35 degrees Celsius. Want to know the maximum water velocity through this pipe, and also want to know what the heat transfer coefficient is if the pipe wall is subjected to a constant heat flux. And of course, both of these assume I have a fully developed velocity and temperature profile. So for part A, first thing to notice is that I have a Reynolds number of 1500 in my problem. That's less than 2300, which is the transition point between laminar and turbulent flow. So this is definitely laminar flow through this pipe. So next thing I want to do is find the properties of water at this temperature, the bulk temperature of 35 degrees Celsius. So from table A6, page 703, find the density of 993. Viscosity of 7.24 times 10 to the negative fourth, and a thermal conductivity of 0.625. Then I can find the Reynolds number, or the Reynolds number relationship, rho Vd over mu. From that I can find my velocity. So rearrange that, my velocity is viscosity times Reynolds number over density times diameter. So velocity, 7.24, 10 to the negative fourth, kilograms per meter second. Reynolds number of 1500. Divided by density of 993 kilograms per cubic meter, and my diameter of 0.025 meters gives me a velocity of 0.0437 meters per second. Now, in this equation for Reynolds number, that velocity actually indicates the average velocity, and I'm looking for the maximum velocity. Turns out that flow through a pipe, laminar flow through a pipe, my maximum velocity down the center line is twice the average velocity. So to find the maximum velocity, just multiply that by 2, and we get 0.0875 meters per second as the maximum velocity in this case. So solution to part B, for a laminar, fully developed circular pipe with uniform surface heat flux, we have the equation for the Nusselt number. That is just a nice constant. Nusselt number is 4.36. And then to find the heat transfer coefficient, we're looking for H. So Nusselt number, HD over K. Just rearrange that for H. So H is K times nu over D. So K value for water, which we found previously, 0.625 watts per meter degree Celsius. Nusselt number of 4.36. And then diameter 0.025 meters gives me a heat transfer coefficient of 109 watts per meter squared degree Celsius. So second example, have water flowing through a tube, rate of 1.3 kilograms per second, mass flow rate. This water is being heated at 20 degrees Celsius to 35 degrees Celsius, so it comes in at 20, leaves at 35, 2.5 centimeter diameter tube, constant wall temperature of 40 degrees, so my tube, 40 degrees Celsius, heats this water from 20 to 35. I want to know how long of a tube do I need. So obviously as the water flows through here, it's going to be heated up. How long at this temperature of 40 degrees for my pipe do I need for that to happen? So first thing to do here is to find the bulk temperature. This kind of replaces the step of finding the film temperature that we use for the external flows. So bulk temperature is the average temperature of the fluid. I know it goes from 20 degrees at the beginning to 35 degrees at the end. So average of those two is 27.5 degrees Celsius. So that's my bulk temperature in this case. So now I want the properties of water at this temperature. So again, table A6 that we used for the previous example, find the value of K, thermal conductivity of 0.614 watts per meter degree Celsius. Heat, CP, 4,179 joules per kilogram degree Celsius. Viscosity of 8.6 times 10 to the negative 4 kilogram per meter seconds, and a Prandtl number of 5.85. And then next thing to do is find the Reynolds number. So Reynolds number for this flow, rho VD over mu. Now we're not given velocities, instead we're giving a mass flow rate. So mass flow rate is the same thing as density times velocity times area. I don't have an area here, so I put an area in the bottom, and then density, velocity become mass flow rate over area, and density over mu, diameter over mu stay there. And then area is just pi d squared over 4 for my circular pipe. So one of those d's cancels, and left the pi on the bottom, 4 comes on top, and 1 diameter left on the bottom. So another version of the Reynolds number dealing with mass flow rate is 4 m dot over pi d mu. So plugging those numbers in, 4 times 1.3 kilograms per second, pi, diameter of 0.025 meters, and this viscosity of 8.6 times 10 to the negative 4 gives me a Reynolds number of 77,000. 77,000 is bigger than 2300, so because of that, this flow is turbulent. And then now that we know that it's turbulent, for a turbulent pipe flow, assuming this is fully developed and a smooth pipe, we have the equation for Nusselt number of 0.023, Reynolds number to the 0.8 power, Prandtl number to the n power. In this case, n is 0.4 because we know my fluid is being heated up. So for heating, n is 0.4. So I can find now the Nusselt number, 0.023, my Reynolds number of 77,000 to the 0.8 power, 5.85 to the 0.4 power, gives me a Nusselt number of 378. And then standard relationship to find h, k times Nusselt number divided by diameter. So 0.614 times 378 divided by 0.025 gives me an h value of 9290 as my heat transfer coefficient in this case. And then what I need to do to find my heating length is to balance the heat required to heat up my water. So that's m dot Cp, the temperature difference, Tv2 minus Tv1. And that equals this convective heat transfer into the fluid, HA T wall minus Tb. Area in this case is my circular pipe area, pi d times L. So now I need to solve that guy for L. So rearranging, solving for L, m dot Cp, Tb2 minus Tb1, so basically temperature coming out, temperature going in, divided by pi dh, T wall minus my average bulk temperature. And so I have m dot 1.3 kilograms per second, Cp 4,179 joules per kilogram degree Celsius. Temperature going out 35, coming in is 20. Then pi, diameter 0.025 meters. H value we found was 9290 watts per meter squared degree Celsius. Wall temperature 40, then average wall temperature 27.5. Gives me an overall length of 8.93 meters for this to happen. Any shorter than that, it'll come out at less than 35 degrees. Any more than that, it'll come out more than 35 degrees. So follow-up question to finish off. Assumed in the previous example that the flow was fully developed pretty much everywhere inside the pipe. I want to know, is that a good assumption? So basically want to know, where does this flow become fully developed? So I have this fluid coming in at 20 degrees. So the first little part of that is going to be not fully developed. It's going to be the entrance region. But what I really want to know is how long is that in comparison to the overall pipe length. If that entrance region is half the pipe, then it's probably not a good assumption. If that entrance region is only 5-10% of the pipe, then it probably is a fairly good assumption because that entrance region is very small compared to the rest of it. So let's find out how much of this is actually fully developed. So entrance length for a fluid in a pipe, I may have to go back to fluids class for this, but for turbulent flow, entrance length LE is 4.4 times Reynolds number to the 1/6 power times the diameter. And so plugging in the values for the previous example, 4.4 Reynolds number of 77,000, 1/6 power, diameter 0.025 meters, gives me an entrance length of 0.72 meters or 72 centimeters. So I expect the first 72 centimeters of that pipe to be not fully developed, but the remaining over 8 meters will be fully developed. So basically more than 90% of this thing is fully developed. So because over 90% of this thing is fully developed, it is a pretty good assumption.